So, just to begin with some announcements, you should bring a laptop to computer to class starting on Wednesday and for the rest of the semester. We'll use a computer probably about 3/4 of the time of classes from now to the end of the semester. So, it'll be important for you to have a laptop that's got Microsoft Excel installed. That's going to be a tool we use quite a lot for problem solving. The other assignment that you got to work on besides homework 2, which you just turned in, homework 3 is available now on Blackboard, and you have 1 week to finish that one, so it should be submitted to Blackboard before noon on Wednesday the 14th. So any questions about those announcements? Finding unknown interest rates and unknown number of periods in order for break-even to occur. So I've got an in-class exercise that goes along with that. Just as a reminder, the videos that are posted on YouTube have the solution to all of the in-class exercises. And so if you're working on the homework assignment and you don't know how to start, chances are very, very good that there's a closely related problem that we've worked in an in-class exercise. And so I'd encourage you to hold on to the papers that I give you for the in-class exercises, because these will be a really good resource when you're solving homework. And then if there's something in your solution that doesn't quite make sense and you don't know how to tie it between the problem statement and the solution, you can go back to the lecture videos and look at the solutions there. I got some good questions via email during the last week, and I'm always happy to reply to your questions. And I'm able to do that most quickly if you give me plenty of information. So for example, if I'm out and I don't have my textbook or class notes with me and you say, I don't understand how to do problem 7. I may not necessarily remember exactly what was the problem statement or what it is that is confusing you. But if you say, I'm working on this problem, and take like a picture of the problem statement or retype it for me, then even if I'm just like at the movies waiting for the movie to begin or out on a walk or something, I can understand what you need help with if you give me additional information. If you say what you've tried already and maybe what specific thing is confusing you, or take a picture of your solution. So just the point is, the more information you give me about how you need help, the quicker I'll be able to respond. But if you just say that you're confused and don't give me additional info or even tell me about the problem, then I'll have to wait till I'm back in front of the computer and have access to my notes. All right, so in the recordings last week, we covered the idea of an arithmetic gradient. And a gradient is where the amount is increasing by a fixed quantity in successive years. And sometimes gradients are combined with other things like annual series or an individual future amount, and that's what this is. What we see here is the combination of an annual series and a gradient where the increasing amount in successive years is $30. And so the strategy, the problem-solving strategy for how you would find what is the present value equivalent of this option T, the subscript here T, is just saying, you know, this was one alternative that is being considered, and we're trying to find out what's the present equivalent. If you were going to receive a certain lump sum amount now in the future so that you could pay for these costs over time, where, you know, it's 400, then 430, then 460, how much would the amount that you receive at time 0 need to be economically equivalent to this series of 5 distributions over time? So the strategy should be that you break it apart into its component pieces. So there's an annual series in the amount of 400, and then on top of that is a gradient where it's 30, 60, 90, 120. You can see that it's, with each successive year, increasing by the amount of 30. Now, I'll revisit something that was mentioned in last week's lectures, that a gradient starts off with 0g in year 1. So times 0 is the present, year 1 is 0g, which is an amount of 0. So we don't actually see the effect of the gradient until year 2. And so that's 1g, 2g, 3g, 4g, and so on. So to solve this, what you do is you find the present equivalent of the annual series, you'd find the present equivalent of the gradient, and then you'd combine them together. So if I was going to summarize how to do this problem, the first phase would be find P given A, where we have the interest rate that applies here is 12%, so I equals 12%, and N equals 5. This is kind of the abbreviation notation that we've started to use for problems like this, where in the parentheses we're saying what kind of a problem it is, the applicable interest rate, and the number of periods.
Is this lecture posted on Blackboard?
The lecture that we're having right now? No, it's not. I didn't post the notes on Blackboard, but I'll do that after class. So this is a summary of the type of the problem statement, and we can see from the factor table here, the P/A for n equals 5 is 3.6048. 3.6048. So what that means is that P divided by A is 3.6048. So if we're trying to find the value of P, then we would say the present value is going to be the annual amount of 4,000. Oh, that's 400. 400 times the factor of 3.6048. Okay, so let me just get my calculator here. 400 times 3.6048, and that's 1441.92. Now, this factor has 1, 2, 3, 4, 5 digits in it. So that means that my answer will only be accurate to 5 digits as well. So I've got 1, 2, 3, 4, 5. So that's 1441.90 is the value, the present value of this $400 annual series. Now, the second part of it is the gradient component. So if we use this same kind of abbreviation method, this is find P given G. So P/G means find the unknown P with a known gradient amount. The interest rate is 12%, and N equals 5. So once again, we can go to the table and find where is P/G for N equals 5, and this is the 12% table. There would be a completely different table for a different interest rate. Okay, so find P given G, N equals 5, 6.3970. 6.3970. All right, so then that means that the ratio of P to G is 6.3970. So P is the gradient value, which is 30. That's the amount that it's continually increasing, times 6.3970. Okay, so let me find the value of that. 6.3970. It's $191.91. And I have to look in the factor, how many digits are there? 1, 2, 3, 4, 5. So that means that my answer will be accurate to 5 digits as well. So I just leave what I've got already. And so the overall present value, the sum of the P's is the sum of the two. So 1441.90 and and 191 and 91 cents. So the sum total is 1633 and 81 cents. Okay, so the strategy is sometimes it may not be immediately obvious to you that there's both an annual series and a gradient. But you'll get better at that, at sort of identifying how the pieces fit together and then breaking it apart and then solving it in pieces like illustrated in the example. So are there any questions about this process? Okay, now what about a situation like this? What we saw about gradients is that the form of a gradient is the first time you see the extra amount is year 2 of the gradient. But here, the first time we're seeing the effect of the gradient, it says it's year 5. So what we have to do is we have to identify what is like a quasi year 0. In other words, what we know is year 3 on this cash flow diagram. From the perspective of the gradient, we're going to pretend like that is year 0. So to find the present value in the actual year 0, the 2 steps would be, first of all, you find out what's the present equivalent in year 3. Because remember, the way that a gradient works is this is 1g in year 5, 2g, 3g, 4g. So year 4 is 0g, and year 3 is the quasi year 0. So the first step, you'd find P given G as a single lump sum amount in year 3, and then the second step would be to take this amount from year 3 and discount it to year 0. Now the word discount, that's a verb in this case, meaning that the amount will be smaller as you move it backwards through time. So you use the factor find P given F, and if we just go to this table, find P given F, if it was 12%, then you can see that all of these have a decimal that's less than 1. So it means that the present value is going to be less than the future value was, because when you have interest and you're moving forward in time, the amounts increase. When you're moving backwards in time, the amounts decrease. So that's kind of why we call it discounting, when we're moving amounts backwards in time towards the present. Okay, so that's our strategy for gradients, when we have it combined with an annual series or when a gradient is shifted away from the actual time 0. Now the reason why I wanted to review that with you is that if we look at the homework assignment, you're going to notice that you've got that problem that comes up. All right, so here's homework 3, and you have problem 2 is a gradient. The gradient, the first effect of the gradient you see in year 4, and then, so that would be 1g, here's 2g, 3g. So you're going to need to do that same multi-step process on problem 2 that I've just explained through this illustration. All right. So let's move on from gradients then, and I wanted to mention that in addition to the equations that I've just handed out, it's also posted on Blackboard. So these formulas are available for you to access at any time on Blackboard. It's also in your textbook, which hopefully by now you've gotten the textbook. But let me show you here, if you go to equations and factor tables, here are the formulas. And so the formula that's listed here is F divided by P. So if I was going to write it on the board, I'd say that F divided by P is 1 plus I to the n power. And I think another way that I've written it several times in class before is F equals P 1 plus I to the n. So, of course, you've just moved the P from the left-hand side of the equation to the right-hand side of the equation. But for each of these rows, it gives you the equation that you need, for example, to find P given G with the equation method. So that's a pretty complicated formula, but it's P divided by G is equal to, and then all of this is on the right-hand side of the equation to find the present value of a gradient. And this also has several different interest rates with the factor tables. And so here's the 0.5% factor table, 1% factor table, 1.5, 2, 4. I think your textbook may even have more like different interest rates than this. Your textbook may have the 3% table, the 5% table, where this just has a handful of them. So I wanted to point those out, that those are online. All right. Now, we're going to be talking about balance of inflows and outflows and how identifying what interest rate is required to achieve that balance is an important problem-solving strategy for us. And so just think about equilibrium. Balance between inflow and outflows is how you find the unknown interest rate in a lot of these problems. So the present value of the inflows is equal to the present value of the outflows when you've identified some specific interest rate that is discounting the inflows and the outflows to the present. So just as an illustration, there is some interest rate in which a $5,000 annual series for 6 years is equal to $23,000 at the present. Now if you just multiply 6 times 5,000, that's 30,000. So 30,000 does not equal 23,000, but the effective interest means that these future payments are worth less than $5,000 in the present if it's being discounted at some interest rate. So what we would need to find in a lot of cases is, what is the interest rate that would cause these inflows to be equal to this outflow when you discount the future amounts at the interest rate? So that's what we're going to be talking about today, is how to find out whether the cash flow diagram is in balance for a given interest rate. And what is that interest rate? So when we find the unknown interest rate, you need to discount all of the future values to the present at an interest rate that you can change in the spreadsheet. And that's one of the reasons why I'm asking you to bring your computer to class on Wednesday, is you can do these problems by hand, but it's very lengthy and tedious compared to if you're just updating a cell in a spreadsheet and all of the calculations automatically update when you've adjusted the interest rate. So it will save you lots of time. What you do is you discount the future amounts to the present, and then you combine it with whatever was already at the present, and then you keep iterating, meaning changing the interest rate until the inflows and the outflows are equal to each other, meaning that there's balance. Now, when we start to use Excel, we're going to have to, in the equations that we enter, kind of override Excel's default assumption. Excel has a series of financial calculations and formulas that are very useful for us to use, but one of the strange things that they've done is they've programmed in the behavior that if you give it a future value, then the present value equivalent it's going to find of that, it'll report it as a negative. So it assumes, for example, that you are making a payment and receiving money in the future. It changes the sign of amounts. So if you wanted to find out what is the present value equivalent of some future amount without changing the sign, you have to automatically enter, you have to manually enter the negative sign in the formula. So I'll show you that today and remind you in the future, but this is an important thing just to keep in the back of your mind, that for the financial calculations, Excel changes the direction of the cash flow by default. So a negative sign has to be put into the formula. All right, let me give you this in-class exercise, some of which you're going to do on paper, and then some of which I'm going to demonstrate on Excel. And if you've got your computer today here with you already, you're welcome to follow along on the computer. But really, I just intend for you to observe parts D and E But I would like you to solve it by hand at first, just to see what I mean by balance and break even. If there's any extra papers when it gets to the end of the row, please pass it back. I think I can clarify a few things that will be useful. All right, so we can see this thing warm up here, hopefully. Where it says net present value, that means find the value of the amount that's already at the present, which is an outflow of 60,000, combined with the present value of the annual series. So $16,000 every year, take it to times 0 using find P given A. So that's 16,000 every year is an annual series, A. So A equals 16,000, find the P equivalent of that using the factor table. That's the first thing I wanted to clarify. And the other is that the outflow at times 0 is a negative, and the inflows that you're receiving every year are positive. So you'll need to combine them together. So the answer to part B should be $653. Okay, so you can go ahead and continue working on that. I just wanted to clarify what I meant by net present value. Okay, the solution for part B is on the screen if you want to have a look. Diagram, we've got a down arrow at the present and then up arrows each year for 5 years, and then the labels is an important part of this. A equals 16,000, P equals 60,000. I didn't write the interest rate on the cash flow diagram because we have a different interest rate for part B compared to part C. So on part B, we're finding the present value equivalent of the annual series at 10% interest with n equals 5. So you go to the factor table, find 3.7908, and you can see that that $16,000, which repeats every year, has a present equivalence of $60,653, and then you combine that with the outflow of $60,000, so the present value is $653 if the future values are being discounted at 10%. But if you discount them at 12%, then the net present value is negative. So what we're going to look at later in the semester is what happens if interest rates change. Like if you have a loan and it's a variable rate loan that can adjust over time, if your loan interest rate goes up, then your project may go from a profitable project to a money-losing project, because that means that a greater share of your profits are going to have to go to cover interest. So here, it asks the question, the net present value when you got 10% and when at 12%, what that means is that the interest rate that causes equilibrium is somewhere between the two. Remember that picture of the rocks that are balanced? And it says sometimes you'll have to find the interest rate that means that there's a balance between inflow and outflow. Well, it's not balanced at 10%. It's not balanced at 12%, but somewhere in the middle is an interest rate that makes the inflows and the outflows equal to each other. And that's what I'm going to show you using Excel. Let me just bring up Excel spreadsheet here. And if you'd like to follow along, you can, but I'm really just intending for this to be observed rather than done by each of you for today. So I'm going to put I equals, and then put in just like a guess interest rate to begin. So maybe 0.10, 10%. Down here I'm going to have year, amount, and PV of amount. Okay, so the years are 0 through year 5. The amounts were negative 60,000 and then 16,000 for all of the other years. And I want to have those formatted as currency. So I'm going to highlight these cells, and I'm going to go over here to the formatting and change it to currency. And then I don't need to necessarily see the cents. So I'm just going to have it decrease the decimal so that it only shows the dollars. All right, so to find the PV of the amount, I'm going to use a function that's built into Excel called equals PV. And when I click the parentheses arrow, it's going to start prompting me for what it needs to know. So it needs to know the rate, it says. So I'm going to click here on the location that says rate, and I'm going to anchor it by pressing the F4 button. When I press the F4 button, it's going to put dollar signs in front of the B and the 1. That means that when I drag the formula down, it'll always look in this location for the rate. For NPER, that means the number of periods. So that means I need to click on this time location here. I'm going to put in a double comma to skip over the payment field because I want to treat each one of these amounts as just an individual future amount. So I'm going to put a minus sign to manually override its assumption that I told you about earlier. Then click in this location and close parentheses. So this 60,000. So this 60,000 hasn't changed by the formula because it's moving 0 years. But if I now drag the formula down, it's going to apply the same equation to each new row. So for example, down here in the corner, you can see there's like a little bit of a thicker cell. If I drag that down here, it says $16,000 in year 1 if you discount it at 10% per year. In year 0, it's worth $14,595. And if I drag it down again, it's going to be an even smaller quantity because there's additional years that this 16,000 would be discounted. So I can drag it down through the entire series and then find a sum total of those. So I'm adding up all of these together and it's 653. So that's what we had found doing it the manual way. 653 is when you're discounting those future amounts at 10% per year. If I change it to 12%, so 0.12, let me turn on the number lock, 0.12, then it's negative 2,324. So that should be what we got here. Now, it's calculating it to the nearest penny because it has like built-in unlimited accuracy, whereas we were using the factor table, which didn't have that same level of accuracy. So there may be slight differences because of that. All right, so what we want to do to find out what is the interest rate that makes this equal to 0. So let me just say, keep changing the value for I until the sum of the PV of amounts is equal to 0. All right, so I'll do that. Let me change this. It was closer when it was 0.1. So what about 0.11? That's too much. 0.101. That's better. 0.102. That's getting closer. 0.103. Getting closer. 0.104. Almost there. 0.105. I went too far. So I could do it manually and try and get exactly the right amount. But there are built-in functions that will allow me to goal seek if I want. And so let me just show you that. If you go data, what if analysis, goal seek, my goal is I want this to be equal to 0 by changing the interest rate. So when I click OK, it's going to manually change the I value a bunch of times, I guess automatically, until the sum is equal to 0. All right, so this, the interest rate that causes balance between inflow and outflow is 10.425%. Okay, so that's the answer to the question. If we wanted to find out what interest rate causes the inflows and the outflows to be equal, it's 10.425%. If you're not already familiar with Excel, maybe this seems very confusing to you if you don't know some of the tricks that I was using as I was filling in the table, but you'll get better at it. We're going to go over this a lot through the semester, so don't feel overwhelmed, but it would be a great idea to work through those same steps tonight on Excel by reviewing the video. So part E says to use the function equals rate. So let me do that. Equals rate. And now it wants to know the number of periods. So there was 5 periods. Each of the payments was $16,000. Down here in bold, it's prompting me for what I need to give it. The PV was negative $60,000. And then I just close it with a parentheses. And here, if I increase the decimals, it's going to tell me 10.425%, which is the same as what we've got in that other manual way. So there's this function called the rate function. Now it doesn't show you quite as much as doing it manually does, but it's still useful to double check. All right, so let me pause. 4 minutes is how much we've got, and that'll be just the right amount of time to do the second problem, if you haven't already taken a look at that. Okay, in the problem that it's describing, P is 60,000 and A is 8,000. So the ratio of P divided by A is 7.5. If you have 60,000 divided by 8,000, that number is 7.5. Now go to the P/A table, and if you go down through it, the crossover point where 7.5 would fit is between 14 and 15. So what that means is that if you get 14 payments of $8,000 per year, it hasn't yet quite paid off the original investment of $60,000. Once you've gotten 15 payments of $18,000 each year, and when those future amounts are discounted at 10% per year, then the present equivalent exceeds what you had paid the original $60,000 amount. So the ratio of P to A is 6.5, and that fits between the 14th and the 15th year. So let me show you in Excel how that would look if we have I equals 0.1, and I can do this in the 2 minutes that I've got left. Year, amount, PV of amount, and cumulative PV of amount. So the first amount is in year 0, we're going to go through 15 years, maybe beyond, just to look at it. So it's negative 60,000, and then $8,000 each year is the revenue that we get. I'm going to do equals PV. The rate is the 10%. The NPER is whatever year we're on. I'm skipping over that PMT field and the negative of the amount into the future value field. And let me change the formatting of this to currency rather than the default accounting style. Currency. All right. So if I drag that down, I find out the present equivalent of each of those future amounts, and then the cumulative amount is just the previous year's cumulative amount plus how much you earned that year. So the crossover point where it goes from negative to positive, you can see in the 14th year it was negative, and then the 15th year it goes to positive. So this is an analysis called break-even analysis that tells you how long do you need to be getting revenue to pay off your original investment. And we'll spend more time coming back to this later, but I wanted to give you the initial taste of it. So that's all the time we've got for today. Remember that homework 3 is available to you now on Blackboard. So I'd encourage you to get an early start on that. I'll see you in class on Friday.